All right, hello everybody. We're going to be looking at chemistry. We're going to go to lesson 8, accuracy and precision. Also go to support materials and you will see the PowerPoint for this lesson. All right, so we're basically understand accuracy, precision. We're going to work on percent error. We're going to do the significant digits part. That will be tomorrow. So accuracy and precision and error. What confuses a lot of people is this idea that the word accurate and the word precise, or accuracy and precision, are talking about two different things. So it's possible to have accuracy and precision at the same time. It's possible to be accurate and not precise. It's possible to be precise and not accurate. For example, if I weigh 165.2345 pounds, okay, that's my exact weight, but my scale only measures it in quarters of pounds, it would say I'm 165 and a fourth pound. So see, is the scale broken? No, because if I weigh 165.2345 and the scale can only measure in quarter of a pound, well, 165 flat is not as good as 165 and a quarter. 165 and a half is not as good as 165 and a quarter. Out of everything the scale is able to do, saying 165 and a quarter is the closest to reality, but it's still a little bit off. There's an error. And the error is that the object I'm using to measure can't be exact enough or precise enough. Okay, so the idea here, in order to limit error, you look for two things: accuracy and precision. What accuracy is just a measure of error. So accuracy is being wrong or right. So this scale is accurate. Okay, is the scale wrong? Is the scale broken? No. It's accurate. It's saying what it should if it can only go by quarters. But the issue is precision, which is the exactness of your measurement, and these are not the same thing. So the scale is accurate. It is saying the right, out of all of its options, it's saying the correct option. The problem is the scale is not precise enough. It only goes by 165, 0.0, 0.25, 0.5, 0.75. That's going by quarters. Okay, it can only do that. It can't go 0.2345. So the issue is that it's not precise. So accuracy is just if you're wrong or right. Precision is if you're very specific about what you are saying. So if an object weighs 5.234 grams, and you say it weighs 5 grams, look at what you did there. Are you wrong? Are you telling me, like, does that make me believe that you don't know what you're talking about, that you didn't measure this object? No, not at all, because 5 is a better answer than 1, 2, or 3, or 4. 5 is a better answer than 6, 7, 8, 9, 10, 11. So if you're just going by just in what's in the ones place, by how many whole grams you have, it's true, you have 5 whole grams. So you're being accurate. However, are you being very specific in your answer? No, you're not. You're saying 5.234. I'm sorry, you're saying 5, you're ignoring the 0.234. So if you would have tried to tell me the decimals, then you probably would have ended up being wrong. Okay, so see, you're accurate when you just say 5, but you're not precise. You're not saying something specific. Okay, what about this? The object weighs 5 grams, and you report that it weighs 6.54334 grams. So first off, are you wrong or right? You are wrong. You are not accurate. But are you saying something very specific? Yes, you're being very specific. So you are precise. You guys understand that? Precision has nothing to do with being wrong or right. You can be very wrong, but very precise. Precise is if you're very specific about what you're saying. Accuracy is if what you're saying is considered wrong or right. All right, so it's kind of an idea of the bow and arrow. So the idea here would be, if you're just aiming for the bullseye or for the whole thing, You just want it to be somewhere yellow, red, or gray. You don't care. This is accurate, right? If I'm just saying, hey, I'm just trying to hit the target. Anywhere on the target, I'm happy. Well, then I'm being accurate, but I'm not being very precise. I'm not specific about where I'm aiming. I'm just kind of hitting it where I hit it. So you see, that's kind of how you can cheat the system. If you want to always be right, then just say super vague stuff. I mean, and that's what people will do. They'll try to sound smart by being as vague as possible. So like, oh, I could make a bold prediction that somebody from the NFC is going to go to the Super Bowl. Well, of course they are. Super Bowl is an NFC and AFC team. So I could make some vague prediction, not get specific, and I'm right because what I said is not specific. Poor accuracy, good precision. With this one, I'm very specific about where I'm aiming. I'm aiming for right here. And look at how I'm doing. I'm always getting the exact same spot. So I got this tight little cluster. If this was over here, man, I'd be doing good. So I'm aiming for this right here. I just am a bad shot. I'm not accurate. I always take my bow and for some reason, when I pull it back, I pull up into the right or something, right? So I'm aiming on the money, but I pull up into the right. So that's why even though I'm very narrow in where I'm aiming, I'm precise when I'm aiming at, my aim is off, so I'm not accurate. And then here, I'm aiming at a specific spot, and I'm hitting that spot, so that would be accurate and precise. Okay, so before we do these calculations right here, let's look at these questions. If I get home at 5:15, and I said I was going to get home after 5. In fact, let's do this. I want you guys to go through and try to do 1, 2, and 3. Try to do the first 3. Press pause, try the first 3, and then press play. So if I actually go home at 5:15, I said I was going to get home after 5. Are you wrong? No, you're right. So I was an accurate statement. I'm going to get home after 5. Show up at 5:15, I was accurate. However, was I very specific in when I said I would get home? No, I left my room a lot. I left myself a lot of room. I just said after 5. So I'm accurate, okay? Just accurate. Is it precise? No, it's not precise because it wasn't something specific you said when you'd get home. If the scale is always 10 pounds below the exact weight of a person. So if you weigh 141 and it says exactly 131, then the scale is accurate. Is it saying the correct information? No, it's not. But does it always say something very specific? Yes. It's always exactly 10 below you. So it's precise. It is not accurate. Okay. Imagine if the scale, you go on it and it just says over 100. It's like, well, okay. That's not accurate. I mean, that's not precise, but now it's accurate. Or you go on it and it says over 200. Well, now it's being vague, so it's not precise, and it's being wrong, so it's not accurate. All right. So if you are 18 years and 25 days old, and I say that you're not even 17 years old yet, my statement is, so first off, am I very specific in what I'm saying? No. It could be 13, 14, 15, 16. I'm just saying under 17. So no, I'm not precise. Am I accurate? You're over 18. I said you're under 17. Am I wrong or right? I am wrong. So it's not accurate. So we'll say not precise, not accurate. Okay, now what I'm going to do is I'm going to go over what we're going to do here. What we like to do in science is whenever we do an experiment or use a instrument, we'll go with an accepted value, which is what we should expect the answer to be. And then observed value is the answer that we actually come up with. So I guess I could make you think about it like this. Observed is what we're testing if it's wrong or right. Accepted is what we know should be the correct answer. So what you'll do is you create this formula where you do the absolute value of observed minus accepted. Or in other words, that just means take the difference between your two values and divide them by what it should have been. Multiply by 100, you'll get a percent. So for example, if you measure the mass of a product to be 3.80 grams, in your calculations, you expected to obtain 3.92 grams. What is the percent error of your work? So what you'll do for this, you measure it to be 3.8, but it was supposed to come out to 3.92. Okay, and this, what we'll do when you calculate something ahead of time, that's what should have happened. So in this case, I mean, imagine if you go to cook something, you can calculate, you'll have a recipe, right? That says like this amount of butter and this amount of flour and this amount of chocolate chips, and it'll make this exact amount of cookies. That's the expected or the accepted value. And then however many cookies you actually end up with is your observed value. And what happened? Your little brother ate some or something messed it up. So in this, what we actually get, the 3.80 is the observed value. And the 3.92 is the accepted value. That's what should have happened. So then what we need to do in order to figure out, so observed is what we ended up getting, 3.8. Accepted is what we should have got, 3.92. So what is the error? How off am I? So what you'll do for this, let's go, let me pull up a calculator so you see what kind of things I'm doing here. So what we do for this is we go and look at the formula. We'll do observed minus accepted. And then it says absolute value, which just means that whatever answer you get, just make it positive. So when we're right here, we're going to do the observed was 3.8 minus the accepted, which was 3.92. Oops, I'm sorry, I'm messing this thing up. I got my keys all messed up on this. Okay, let's try this again. So we have 3.80 minus 3.92, and we get negative 0.112. Look at the formula, though. You just always, this is absolute value right here. So whatever the difference between them is, just keep it positive. So the error in this, it is wrong by exactly, ignore the negative sign, 0.112. So how wrong was I in this thing right here? I was off by 0.12. So then what we'll do is we'll do 0.12 divided by what was accepted, which was 3.92. So we'll take 0.12 divided by 3.92 and then times 100. And so we're 3.06% is our error. So we were off by 3.06%. So like what will happen is you'll have an experiment. You'll say like, hey, we're trying to create crystal out of these super expensive materials. And you might say we're only willing to have a 1% error. Meaning if these materials are supposed to make 100 grams of crystal, we're only willing if you're off by a gram. Right? Because if it's too little, you're wasting the materials. If it's too much, it's impure. So like the percent error is how off you're allowed to be in the experiment that you do. So with that, I want you guys, here's how we're going to do this. You guys go ahead and try to do the rest of the problems here. Whenever I go to my whiteboard, when I do that little bubble thing, when I do that bubble where you can see what I'm doing, it ends up, the calculations end up looking backwards for some reason. So until I fix that setting, here's how we're going to do this. I want you guys to do the rest of these problems. I'm going to make a short separate video that will be at the bottom of this where I'll just work out these problems so you can double check yourself on how to do it. So finish this thing. When you're done, you can watch the video at the end.